Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In the last lecture, we have studied about the series solution of the differential equation. In this, and also we have solved some examples. So, in continuing to that lectures, today we are going to solve some more problems related to that. So, example number 1. Find the series solution of the differential equation 2x square y double dash plus 2x square minus x y dash plus y is equal to 0, equation number 1. The solution, the given equation can be written as y double dash plus 1 minus 1 by 2x y dash plus 1 by 2 x square y is equal to 0, where px is equal to 1 minus 1 by 2x and qx is equal to 1 by 2x square, which are not regular at x is equal to 0, but xpx and x square qx are regular at x is equal to 0. Then x is equal to 0 is a regular singular point. Let us assume that the solution be y is equal to summation r is equal to 0 to infinity ar x to the power m plus r, equation number 2. Now substituting 2 in equation 1, we get 2 summation r is equal to 0 to infinity m plus r minus 1 ar x to the power m plus r plus 2 r is equal to 0 to infinity m plus r ar x to the power m plus r plus 1 minus implies summation 0 to infinity 2m plus 2r minus 1 m plus r minus 1 ar x to the power m plus r plus 2 summation r is equal to 0 to infinity m plus r ar x to the power m plus r plus 1. This is equal to 0, equation number 3. Now we equate to 0 the coefficient of the lowest degree term x to the power m and get the initial equation as 2m minus 1 m minus 1 a naught equal to 0, which implies that m is equal to 1 1 by 2 since a naught is not equal to 0. Therefore, two independent solutions can be obtained by taking m is equal to 1 by 2 and 1. The recurrence relation is obtained by equating to 0 the coefficients of the general term x to the power m plus r in equation 3 as 2m plus 2r plus 1 m plus r ar plus 1 plus 2 m plus r ar is equal to 0, equation number 4. Therefore, ar plus 1 is equal to minus 2 ar over 2m plus 2r plus 1, and for half m is equal to half, we have ar plus 1 is equal to minus 2 ar over 2r plus 2 is equal to minus of ar over r plus 1, and therefore a1 is equal to minus of a naught, a2 is equal to minus 1 by 2 a1, this is equal to a naught over 1 into 2, a3 is equal to minus of a2 over 3, which is equal to minus of a naught over 1, 2, 3, and so on. And therefore, one solution is y1 is equal to x to the power m summation r is equal to 0 to infinity ar x to the power r. This is equal to a naught x to the power half 1 minus x plus x square by 2 minus x cube by 2 into 3 plus up to plus and so on. Next, for m is equal to 1, the recurrence relation 4 gives ar plus 1 is equal to minus 2ar over 2r plus 3. Then a1 is equal to minus 2 by 3 a naught, comma, a2 is equal to minus 2 a1 over 5. This is equal to 2 square a naught by 3 into 5. a3 is equal to minus 2 a2 over 7. This is equal to minus 2 to the power 3 a naught over 3, 5, 7, and so on, etc. Thus, the second independent solution y2 is given by y2 is equal to x to the power m summation r is equal to summation r is equal to 0 to infinity ar x to the power r. This is equal to x a naught within the bracket 1 minus 2 by 3 x to x plus 2 square x square by 3 into 5 minus 2 cube x cube by 3 into 5 into 7 plus up and so on. Therefore, the general solution of the given differential equation is y is equal to a y1 plus b y2, where a and b are obtained are arbitrary constants. Now the next problem, solve the differential equation x 1 minus x y double dash plus 2 1 minus 2x y dash minus 2y is equal to 0 using Frobenius method, that is series solution. Let its series solution be y is equal to 0 to infinity ar x to the power n plus r. Putting the values of y, y dash and y double dash in the given equation, we get summation ar m plus r, another bracket, m plus r minus 1 bracket close, x to the power m plus r minus 1 minus summation ar within bracket m plus r bracket close. Now another bracket start, m plus r minus 1 bracket close, x to the power m plus r plus 2 summation ar m plus r into x to the power m plus r minus 1 minus 4 summation ar m plus r x to the power m plus r minus 2 summation ar x to the power m plus r is equal to 0, or summation 0 to infinity ar m plus r plus 1 x to the power m plus r minus 1 minus 0 to infinity ar m plus r plus 1, another bracket, m plus r plus 2 into x to the power m plus r. This is equal to 0. Equation number 2. For indicial equation equating to 0 the coefficient of x to the power m minus 1, we get a naught m plus 1 is equal to 0, implies m is equal to 0, comma minus 1, a naught is not equal to 0. Equating to 0 the coefficient of x to the power m plus r, in equation 2 we get a r plus 1, m plus r plus 1, m plus r plus 2, minus of a r m plus r plus 1 m plus r plus 2 equal to 0, implies a r plus 1 is equal to a r, where r is equal to 0, 1, 2 and so on. Therefore 2 becomes y is equal to a naught x to the power m plus x to the power m plus 1 plus and so on. This is equal to a naught x to the power m over 1 minus x. Hence the solution for m is equal to 0 is y is equal to a naught 1 plus x square plus and so on, which is equal to a naught over 1 minus x. For the other solution, dy by del y by del x is del y by del m is equal to a naught x to the power m over 1 minus x log x. Therefore del y over del m at m is equal to 0 is equal to a naught log x over 1 minus x. Thus the complete solution is y is equal to a over 1 minus x plus b log x over 1 minus x, or y is equal to a plus capital B log x, another bracket, 1 plus x square and so on is the required solution.